Hi, and welcome back. We're on page 2 of the practice exam from summer session 18. This is the nomenclature page. We're going to be drawing two chiral molecules that are diastereomers of each other. The relationship between diastereomers is the type of stereoisomer where we have some chiral centers that have the same configuration and others that do not. But otherwise, these compounds, the two compounds, have the same molecular formula and the same connectivity. So I'm going to start simple with just a 6-carbon chain, and I'm going to give it 2 chiral centers. I'm going to make one of them wedged, and I'm going to put, I don't know, like a bromine on there. And then let's do another one wedged here. We'll also put a bromine there, why not? And we want to make sure, first of all, that it's not a meso compound because it is not symmetric. If I had another one right there, that would be a meso compound. But it's not, because that's not my example. In order to make it into a diastereomer, I have to keep one chiral center the same, so the configuration here on carbon 2 is the same as in the left structure, and then the other one is going to be different. So these two are diastereomers of each other. We're going to show the RS designation of each one. This is our first chiral center. Bromine has a first priority because it goes by atomic number. This over here gets priority 2 because it's a carbon that's attached to more carbons, and this is priority 3 because this carbon is just attached to hydrogens. We're looking at this the correct way because the hydrogen's pointing back. So this is an R center because it's counted 1, 2, 3 counterclockwise, and that's the right way, and that's the R designation. R center. Next one. This guy. 1, 2. This carbon here is attached not only to other carbons, but also to that bromine. So that gets priority 2. Over here is priority 3. Once again, we're looking at it this correct way because the hydrogen's pointing back. And now it goes 1, 2, 3, and this should have been pointing to the 2, not to the hydrogen. But that's counterclockwise, so this is going to be an S center. S. All right, we can speed things up a little bit on this next one. That's R, because we assigned it on the previous one, and we switched the wedge to a dash, so this is R again. And this is just one of many examples of diastereomers in two compounds. Next, we're going to be looking at or drawing structures that go along with these compounds names. The first one is a bromophenol compound. A phenol is when you have a benzene ring with an OH group or an alcohol, that's specifically phenol. Ortho means it's going to be one carbon away, so it's either this position or this position here. It doesn't matter. There's only one. I'm going to put it down here for space sake, and that's orthobromophenol. Metachlorobenzoic acid is next, and the way you might recognize this is metachloroperoxybenzoic acid is the reagent that you use to turn an alkene into an epoxide. That's what MCPBA is for, just in case you wanted to know that. And I'll make it trans. So again, metachloroperoxybenzoic acid is different from benzoic acid, which is where we have a carboxylic acid directly off of the benzene ring. Meta is when you have 2 carbons away on that ring, and either one of those would be fine. I'll put the chlorine right there. Next one is Z-heptene. We're going to make this a cis double bond. So since we know that's going to be happening, we're going to start with that double bond. We'll number it so that this is number 3 and 4, and then we'll go in either direction and add it up and make sure we have 7 carbons total. That's going to be carbon 2. That's carbon 1. We have 4, this is 5, 6, and 7, and that's all there is to it for Z3-heptene. Next, we're going to be looking for aromatic compounds. The criteria for an aromatic compound is as follows. First, it's got to be cyclic. It's big. Second, all of the atoms in the ring must be sp2 hybridized. And then, and only then, number 3, do you use the Huckle Rule, which is 4n plus 2. That tells you the allowable number of electrons that would be aromatic. So if n were to equal 0, then that formula would give you 2. So that's allowable number of pi electrons. If the n were 1, just an integer, then the formula would give you 6, and so on. But that's probably all we're going to need. So we can see on the first, actually all of these initial compounds, they're candidates because they pass number 1, they're cyclic. This one right here confuses some students who are just rushing things and aren't looking to make sure that those compounds are cyclic to start. So now we're going to look one at a time at the first 5. I'll just put a little X there so we know that we ruled them out. We do have in this compound, all the atoms are sp2 hybridized. This guy here might look sp3 because it has a hydrogen and a lone pair, but the important thing to note and remember is that it can participate in resonance, which means that this carbon atom must have been sp2 hybridized, so that's great. And then we can count up the total number of pi electrons, and those are the ones that do participate in resonance. So there's 2, 4, and 6. And 6 is an allowable number of pi electrons based on the Huckle Rule, 4n plus 2. We can see that 6 is an allowable number of pi electrons. So I'll clean up this a little bit. This is aromatic. Next, I'm sure we could do some resonance structures where we kick these electrons over. Boron is a strong or good Lewis acid. It has an empty p orbital. It is sp2 hybridized, and that's great, but we don't have the right number of pi electrons to actually make that happen. There's only 2, 4. So this is not an aromatic compound, unfortunately, for that compound, I guess. Next, we have classic compound benzene has 2, 4, 6 pi electrons, and sorry for going out of order, but it already passes the cyclic and sp2 test. So that is aromatic. This next one is cyclic. All of the atoms are sp2 because they're all involved in double bonds. Is a short way of checking that out. However, you have 2, 4, 6, 8 pi electrons. That doesn't fit the Huckle Rule. And the Huckle Rule might maybe to like go to the next level. If you had 2 plugged in for your n and you did that, it would be 10. So 8 does not fit. 8 is not an allowable number of pi electrons. So this also no. And then we get to this cyclopropene example. Since there's no lone pair or carbocation shown on that top carbon, you'd assume that it has 2 hydrogens, which means that is sp3 hybridized. So this can't be an aromatic compound either, and only 2 of them are actually aromatic. Part D has you drawing the most and least stable conformations of butane. So let's start by drawing just regular old butane, and we're going to refer to the bond rotation around the 2-3 bond. We have 2 hydrogens, and I'm going to explicitly show these because this is going to help us with the Newman projection. And we're going to do that. We're going to have our circle line dot. Let's see, we're going to number these guys. So we know that that dot there in the front is 2, and the one in the back is 3. So carbon 2 has a methyl group and 2 hydrogens. Carbon 3, we're going to spread out like this, and this is going to be our more stable conformation, because we're going to have it be staggered. What we have connected to carbon 3 is once again 2 hydrogens and a methyl group, and we want those methyl groups to be as far apart as possible. And that's how we do it. Methyl groups on totally the opposite side. This is the more stable conformation of butane. The less stable conformation is when we have those 2 methyl groups right next to each other. So we'll just first of all draw this eclipse. We'll have the 2 methyl groups up on top, but they could be towards the left or they could be towards the right. That's not a big deal. It's more about having 2 hydrogen-hydrogen eclipsing interactions, and 1 big methyl-methyl eclipsing interaction. And so when we say what the more stable conformation is avoiding, there's actually 2 right answers for this. We would Be looking for gauche interactions would be something that would be specific for a stagger conformation. If those two, say if like the methyl group is right here, there would be gauche interactions there, but they don't occur with a hydrogen. But really the big thing that we're avoiding for the more stable conformation are any eclipsing interactions, or the proper term would be torsional strain, or eclipsing is pretty much just as good. All right, and that's what's happening with the conformations of butane. We then go on to our next conformational analysis problem, 1-Tert-Butyl cyclohexane. Now this is going to be a chair problem. I'm going to start by drawing the regular hexagon structure though, 1-Tert-Butyl. We're going to have the least state, going to draw the two conformations and then indicate the less stable one. I'm going to start by drawing our best chair. That's not my best chair, where we're going to have no vertical lines and no horizontal lines. And one conformation, if I were to put the tertiary butyl group pointing up here, it would be axial. In order to actually do a proper ring flip, just as like a quick little reference point, I'll just number them all. So you can see what actually happens in the ring flip. We're going to flip the head of the chair down and flip the ottoman up. That is going to make the other type of ring, right? So now our carbon 1 is pointed down, 2, 4 is up, 5 and 6. Now we want to be very consistent to show the two conformations. So we still want our T-butyl group to be up, but in any ring flip, any axials go to equatorial. So here we go. These are this is our tertiary butyl group now pointing up and equatorial. The more stable conformation is specifically going to be avoiding 1,3 diaxial interactions between the tertiary butyl group and the hydrogens that are 3 carbons away. So that would be 1,3 diaxial interactions between those two. It'd be easier to show like this. And these would be 1,3 diaxial interactions from carbon 3 to that tert-butyl group. Diaxial interactions. Right, so we have our chairs in pairs. We did our ring flip, and we show that our big substituent went from axial to equatorial. This is going to be the least stable, because that's what you're asked for, because of those 1,3 diaxial interactions. That's page 2.